Okay, so back when we were talking about inverse trigonometric functions for the first time, there was a very particular kind of exercise that we encountered. Namely, something like this. We would see a trig function with an inverse trig function inside of it, and then the claim was that we could write this in a quote-unquote algebraic form. So algebraic form in this context, meaning that we could rewrite this in such a way that no trig functions or inverse trig functions appear. So, let me remind you how we would go about solving something like this. So let theta be arcsine of x, just so that we don't have to keep writing that out every single time. And in particular, notice that because the arcsine function only outputs between negative pi over 2 and pi over 2, you can interpret theta as being an angle between negative pi over 2 and pi over 2. And consequently, when you take the cosine of that angle, it's always going to be positive, right? You look at the graph of the cosine function. Between negative pi over 2 and pi over 2, it's always positive. So, we can set up this Pythagorean identity, sine square plus cosine square equals 1, and then solve for cosine theta. And that would be what we want, right? We're looking for cosine theta. So just move the sine square to the other side, take square roots, and because we have already established that this cosine is positive, we take the positive branch of the square root. So we don't have to worry about putting a plus minus here. And then, because theta is an inverse sine of x, taking the sine of theta, well, it just cancels out the arcsine so that we just get x left over. So sine square theta is x squared by definition. So there we go. So the cosine of arcsine of x is equal to square root 1 minus x squared. That's how we could write something like this in a form which doesn't have any trig functions in it. So this idea of a duality between trig functions and algebraic functions that look like this, with a big square root and a square in them, this idea underpins the technique of trigonometric substitution. Because, say for instance that we were looking at an integral, and this term, square root 1 minus x squared, appeared in the integral. Well, certainly it would be easier to deal with a cosine theta in that integral, instead of this big ugly square root term. So if we make a substitution, say if we introduce a new variable theta, such that theta is equal to arcsine x, or equivalently, such that x is equal to sine theta, and such that we can guarantee that the cosine is going to be positive, then we can replace the square root 1 minus x squared with cosine in the integral. And hopefully, after you do all the requisite bookkeeping, one would hope that the integral you end up with is actually easier to do than the integral you started with. Right? Because you're replacing this big ugly square root term with a single cosine term. So indeed, that is the idea behind trig substitution. You see an integral that has big ugly square root terms in them, and provided these big ugly square root terms are derived from a Pythagorean identity in some sense, then we can apply a substitution like x equals sine x, and then replace that ugly term with a trig term instead, and hopefully obtain something easy. So, that is just one example of a substitution that we can do. I have summarized below some of the more common substitutions that we make. So, So if we introduce theta such that x is equal to a sine theta, where a is just any number, it's, just adds a little bit of generality, where theta is between negative pi over 2 and pi over 2. Well, if this is the case, then we can say for certain that square root a square minus x square is going to equal a cosine theta, for exactly the same reason as up here above. It's a consequence of the Pythagorean identity. And why do I have to specify that theta is between negative pi over 2 and pi over 2? Well, that's just to guarantee that this guy is going to be positive. That way, we can just take the positive branch of the square root, and we don't have to worry about it. So a similar situation is happening here. So if you let x equal a tangent theta, and theta is within some range, then this dude reduces to a secant. If you let x equal a secant theta, and you let theta be within some range, don't really worry about this bit, then we can say that this square root term is equal to a tangent theta. So don't worry too much about the range of the thetas that we're dealing with here. We're just specifying this range of thetas so as to guarantee that we can take positive branches of the root. So that's just a technical consideration. So let me just briefly show you. So we know that this first identity is due to this Pythagorean identity up here. Let me just quickly verify that these other two hold as well, because indeed, that follows from the other Pythagorean identities. So, here, if x is equal to a tan theta, where, a is just any positive number, then take a look at this dude. A square plus x square. Well, that is going to be square root a square plus x is equal to a tan theta, so this becomes a square tan square theta. Now I can factor that square root out, or I'm sorry, I can factor the a squared out. But now, we have a Pythagorean identity that says that 1 plus tan square is equal to secant square. So square root of a squared is just a, because that's positive. And then we have square root of secant square left over. And, yep. So then that just gets squared away as well. Technically, I should put absolute value secant here, but I chose the thetas such that secant is always going to be positive, right? You can verify for yourself that if theta is between negative pi over 2 and pi over 2, then secant's always going to be positive. So we don't need to worry about the signs here. And a similar proof for this one as well. We're just using that same trig identity. Anyway, okay, so sort of like with integration by parts, really the only way to gain any sort of proficiency with this technique is just to do a whole bunch of examples. So let's go. So evaluate root 9 minus x squared over x squared dx. So we want to use a trig substitution. So which of these three forms corresponds to this dude? Well, this dude sure looks like a squared minus x squared. So that corresponds to this form here, which means that we should introduce the substitution x equals a sine theta. So since we have an expression of the form root a square minus x square in the integrand, we use the substitution x equals a sine theta, so that we may write a square minus x square equals a cosine theta, right? Because then, if we replace this term with a cosine, then one would hope that it ends up being easier to look at, or easier to work with. So in our case, a squared is equal to 9, so that means a is going to equal 3. So let's let x equal 3 sine theta. Now, anytime you do a substitution, so remember when we were doing u substitutions, every time you introduce a substitution, you then have to take the derivative because you need to get the d terms out of it. So same deal here. So x is equal to 3 sine theta, so we have to differentiate that to get our d terms. So dx d theta is equal to, so the derivative of sine is just cosine. And consequently, we need to solve for dx. Well, that's easy. Dx is just 3 cosine theta d theta. Like so. And now we can start plugging things into our integral. So on the top, we have square root 9 minus x squared, but the whole point of making our substitution is so that we can replace this thing with a cosine theta. So instead of writing all of this, we write 3 cosine theta instead, right? Because a was equal to 3 in this case. Over x squared. Well, okay, but instead of x, we have 3 sine theta. So x squared becomes 9 sine square theta. And then instead of dx, I write all of this. So this is what we end up with after plugging in the substitution. Like so. Now let's see what happens. So 3 times 3 is 9, 9 in the denominator as well, so those 9s cancel out. So we have cosine squared on top, and sine square on the bottom. Okay, so how can we go about anti-differentiating this thing? Well, cosine over sine, that's the same as cotangent, right? Cotangent squared. Now, we don't really have a formula for cotangent squared, but we do have a formula for cosecant squared. And conveniently enough, there is a trig identity which relates the cotangent square and the cosecant squared. So at this point, I will utilize the identity 1 plus cotangent squared equals cosecant squared. So in particular, this means that cotangent square is cosecant square minus 1. Right? Now this is good, because antiderivative of 1 is just theta. Antiderivative of cosecant squared is minus cotangent theta. That was one of our formulas. That's one of those things where it's literally just a derivative in reverse. So we get minus cotangent theta minus theta plus c. And now the anti-differentiation has been accomplished. So, we're not done yet, because our original integral was written in terms of x, so that means our final integral needs to be written in terms of x as well. So now we need to rewrite this to be in terms of x. Well, let's see. For the theta, that shouldn't be too hard, because x is equal to 3 sine theta. So if we solve this for theta, we get sine theta is equal to x over 3. And so to get theta by itself, we take the inverse sine of both sides. So theta is equal to the arc sine of x over 3. So there's that. There's the theta taken care of. What about the cotangent theta? So to do this, we're going to take advantage of the Pythagorean identity again. And, well, what's the only Pythagorean identity that has cotangent in it? Well, this one again. Yeah. So, in particular, we want to figure out what cotangent is because we want to plug something into this right-hand side. So let's solve this for cotangent. And don't worry about the square roots here. We're just going to assume that theta has been chosen such that everything is positive. So this is square root. Yeah, there we go. Right, so subtract 1 and then take the square root. Well, how does this get us anywhere? What the heck is cosecant? Well, remember, cosecant is 1 over sine. So this is, in fact, 1 over sine squared theta minus 1. Now, how does that help us? Well, because we already know that sine is equal to x over 3. That was the case by definition. That's how we introduced this this parameter theta in the first place. So like so. And then we can clean that up a bit. So x over 3 squared is x squared over 9. So then we take the reciprocal of that. So 9 over x squared minus 1. And then because I feel like it, I want to put this underneath a single square, or I want to write this as a single fraction rather. So common denominator is x squared, 9 minus x squared, like so. And then we can square root the top and the bottom to get like so. Okay. And again, those of you who remember their algebra should be saying, wait, shouldn't this be absolute value x down here? Don't worry about it. Don't worry about it. we are assuming that all of the variables are chosen such that everything becomes positive. And you can trust that everything works out. Okay. So for our final answer, we just put these things in here. So our final answer is this equals this, but then instead of cotangent, I got all of this. There we go. And then instead of theta, I have this. And there we go. So yep, that's it. So quite a lot that goes into this. Like I'm not going to claim that this is super easy or straightforward. Yeah, like I don't know what advice to give other than to just follow the examples. But yeah, this is how it goes. I mean, we are at the point now where you certainly need to have all of the trig identities, certainly the Pythagorean identities, well known. because these are coming up constantly. So yeah, and also, you know, I wouldn't blame you if you, for instance, don't remember that the antiderivative of cosecant square is minus cotangent. I mean, that's one that even I don't think I've really memorized consistently. So that's why it's a good idea to have your like trigonometry cheat sheet on hand when you're working on this stuff, and the common derivatives and integrals cheat sheet on hand as well. Okay, next. So for this one, notice that we have a big square root x squared plus 2 squared. So which of the substitutions corresponds to that? Well, that's going to be this one. So we need to make the substitution x equals a tangent theta. So since square root x squared plus 2 squared appears in the integrand, we make the substitution x equals 2 tangent theta, so that this dude becomes, let's see, so that this dude becomes 2 secant theta. Now, before we move on, we also need to figure out the d terms. So if we differentiate this, dx is equal to 2 secant squared theta, d theta. Right, so remember the derivative of tangent is secant squared. Okay, so let's start plugging things in. So, let's see, so on the bottom we have x squared. X is 2 tangent theta, so this becomes 4 tan square theta. Here's the square root x squared plus 4. That all becomes 2 tangent theta. Or I'm sorry, 2 secant theta. And then instead of dx, we have 2 secant square theta d theta. So that's the substitution part finished. Now let's see. 2 over 2, those cancel. So we have a 4 left over. So we can factor that out. One of these secants is going to cancel. So on the top, we have 1 secant left over, and on the bottom, we have 2 tangents left over. Right? Just double checking. Yeah, so that's all proper. Okay. Secant over tangent squared. How the heck can we deal with this? Well, when I see something like this where it's not immediately obvious what the heck is going on, what I like to do is to convert everything to be in terms of sines and cosines. So, like, remember, secant is the same as 1 over cosine, and tangent is the same as sine over cosine. So let's just convert that and see if that makes things any clearer. So recall, secant is the same as 1 over cosine, and tangent is the same as sine over cosine. So this becomes, oh my goodness. Let's see. So that secant becomes 1 over cosine. And then, since tangent is sine over cosine, but we have 1 over tangent, that becomes cosine over sine. And that is all squared as well. So, this wasn't a terrible idea, because we can see now that one of these cosines is going to cancel. So we have one cosine on top and two sines on the bottom. Okay. And now we are in the position to just do an ordinary u substitution, because if I let u be sine, well, the derivative of u is cosine, so that means this cosine up here is going to end up getting canceled out. Right? So if we let u equal sine, then du is equal to cosine d theta, and consequently d theta is equal to 1 over cosine du. So we're two substitutions deep now. So we did the first substitution to be in terms of theta, and now we have another substitution in terms of u. So let's see. So cosine on top. Sine has become u, so now we have u squared on the bottom. And then instead of d theta, we have 1 over cosine du. So these cosines cancel, as desired. Okay, so finally we have obtained an integral where we can just hit this with the power rule. So this is u to the power negative 2, so we end up with u to the power negative 1 divided by negative 1, so there, let me just write it like that. Yeah, that's it. Well, that's it as far as the antiderivative goes. So now we need to start rewriting everything to be in terms of the original variables. So first off, u was equal to sine. So u is equal to sine, and now what was sine theta? Well, okay, we don't know what sine theta was, but we do know what tangent theta was. So tangent is the same as x over 2. Now, can we get sine out of that? Well, yeah, so we're going to have to use a Pythagorean identity. So let's see, we know that tangent theta is equal to x over 2. So to get sine theta, use the identity. Well, let's see. Which of the Pythagorean identities has both sine and tangent in it? Well, it's got to be this one. It's got to be this one, right? Because cotangent, well, that's 1 over tangent. Cosecant, well, that's 1 over sine. So this is the same as, you know, having an identity that's in terms of sine and cosine. Like so. Okay. So tangent is x over 2. So 1 plus 1 over x over 2 squared is equal to 1 over sine squared. So now we just need to solve this for sine. So let's see. So x over 2 squared is x squared over 4, then take the reciprocal. Let me go ahead and push this together into a single fraction while we're at it. So there's that. Now let us reciprocate both sides. So sine square theta is equal to the reciprocal of this. And now we just need to take square roots. Yeah. So x over root x squared plus 4, like so. So square root of x squared became x. And again, don't worry about absolute values. Don't worry about plus minuses. We are assuming that we are choosing the substitution such that everything works out nicely. So, our final answer is this, where instead of sine, we're going to write all of this junk. So 1 over sine, so that means it's going to be the reciprocal of this. And let me just go ahead and put that 4 there. Just looks a little nicer that way. And let's not lose sight of what it is we were doing in the first place. So there we go. So yeah, pretty neat. Yeah, so this technique, I mean, there's a lot going on. There's a lot going on here, and it really requires some degree of fluency in trigonometry, not to mention basic algebra, to be able to do this in a reasonable amount of time. So, you know, take it easy and just follow the examples, I suppose. Now, for this next one, so notice we have a square root x squared plus 4 in here. So just like in the previous example, you might think, okay, well, we've got a square root x squared plus 4, so let's do the substitution x equals 2 tan theta, and then proceed from there. And you can certainly do that, but this is an example that we can actually do with just an ordinary u substitution. So although we certainly can do the trig substitution x equals 2 tan theta, this particular example can be solved more easily with, say, a traditional substitution. In fact, I feel like we've done this one already. Or if not this one exactly, then at least ones that are similar to this. Right? Because, and the reason why is because when we differentiate u, we're going to end up getting a 2x. And oh hey, there's an x that's hanging out, just waiting to get canceled. So this will all work out. So du is equal to 2x dx, and consequently dx is equal to 1 over 2x du. Right, and then there's that x just waiting to get canceled out by this x here. So, you know, this is the sort of thing where if you do tons of examples, you'll just start to recognize the patterns that show up time and time again. So our integral becomes x over square root u, right? Because x squared plus 4 is now u in this context. Replace dx with all of this. That should be du. So x and x cancel. So we have just an integral of minus u to the power minus 1/2, which we can now just hit with the power rule. So let's see. This becomes u to the positive 1/2 divided by 1/2, so that's the same as multiplying by 2. So yeah, like so. Yeah. That's all there is to it. Yep, and then just replace u with what it was. So indeed, in cases like this, a quote unquote normal substitution requires far less work than the trig substitution would. So I'm just calling your attention to that fact, that just because you see something like this, that doesn't necessarily mean that a trig substitution is your only option. Okay. Next, so square root x squared minus 9. So let's see, which of the substitutions would this correspond to? X squared minus 9. So not this one, because we've got a minus x squared. Not this one, because we've got a plus. All right, it must be this one. Square root x squared minus 3 squared, right? Because 9 is 3 squared. So that means we need to let x equal 3 secant theta. So since x squared minus 3 squared appears in the integrand, we do the substitution x equals 3 secant theta, so that this dude becomes, well, let's see, what does that become? It becomes 3 tangent theta. Okay, so let's take the derivative to get our d terms. Mustn't forget that. So the derivative of secant is secant tangent. Like so. And now let's start plugging everything in. So, by the way, I wrote it like this because this is how it was written in the book. I don't really like putting the differential up here like this. I would rather take this differential and put it over to the side, because I like to think of the differential term as being like a delimiter for the integral process. But all the same, occasionally you might see it written like this. So it doesn't mean anything. It doesn't mean anything special. It may as well be over here and have a 1 up here. So let's see. So square root x squared minus 9, that becomes 3 tan theta. And then dx, well, dx is going to become all of this junk. Like so. Okay, so let's see what happens. 3 cancels, 3 cancels, tan cancels, tan cancels. So this just becomes the integral of secant. Well, yeah, that couldn't have worked out better. Now, what is the antiderivative of secant? So this is going to be one which I don't blame you at all if you forget. So just look it up. I think I had this one in my notes for the previous section. It is natural log secant plus tangent. Yeah. Yep. So that's natural log absolute value secant plus tangent. And that's one that either you remember or you don't. Okay. So now we need to rewrite everything to be in terms of x. So with the tangent, we can do that because we know that tangent is equal to all of this junk over 3. And with the secant, oh, we can also do that because secant is equal to x over 3. So actually, no additional work required in this case. So secant is equal to x over 3. Okay. can I make those absolute values look better? Hang on. There we go. So secant is x over 3, and tangent is square root x squared minus 9 over 3. Okay, now we can be done here, but I want to point out one additional thing that you can do in terms of simplifying this. So, I mean, we have a common denominator here of 3, so we may as well push this together to make a single fraction. Like so. Well, now, because of the laws of logarithms, if you have a division inside of a logarithm, that becomes a subtraction outside the logarithm, right? So this is the same as log of the numerator minus log of the denominator, so minus log 3. Now here's the thing. Log 3 is a constant. Negative log 3 is a constant. C is a constant. And C can be literally any constant. So we may as well take this entire term and just call that C. Right? Because C isn't anything in particular. This is just one big lump that represents all of the constant terms that might be over there on the side, right? So by subtracting log 3 from it, you're just getting a different constant. But symbolically, you need not reference that change, right? Because when I write down big C here, I don't mean any particular constant. I just mean the concept of constants. So I can lump these two guys together into a single constant term, and I don't have to feel bad about that. So yeah, so that's one way that you could simplify this. And you could probably see this in a multiple choice response. If I had to guess, they would probably do this. Okay, so finally, let's do an example of definite integrals in this context. Now, what's going on here? Now, we have 4x squared plus 9 to the power 3 halves. So, recall, a power of 1/2, or, any fractional power denotes a root. So in this case, since the denominator of the fraction is a 2, that means that we are indeed taking the square root of this. So in particular, notice that this is so 4x squared to the 3 halves, that is square root of 4x squared plus 9 cubed, right, by definition. So we are, in fact, taking the square root of a big chunk. So the idea of trig substitution should come to mind, right? Anytime you're taking a big square root of something that has a square in it. Now, in particular, which trig substitution would be appropriate? Well, we've got something squared plus 3 squared. So that looks an awful lot like this one, right? But it's not exactly correct, because here we have just x squared, but here we have 4x squared. Well, I mean, that's not a big problem, because this is the same as 2x squared plus 3 squared. Right? Right? 4x squared is the same as 2x squared. So instead of writing x equals, what would the a be in this case? 3. So instead of writing x equals 3 tangent theta, let's write 2x equals 3 tangent theta, right? Because it's 2x which is occupying the same spot that x occupies in the formula. So let's introduce the substitution. 2x equals 3 tan theta. Was it tan? Yeah, it was. Right? No reason that we can't do that. And, oops. So if we do that, what is this term going to end up looking like? So actually, I don't like this cube being down here. Let's put the cube out on the top, because we can do that just as easily. So take this and raise that to the power 3. Right? I mean, algebraically, this is fine. So if we do that, then this term here becomes 3 secant theta. Is there anything else that we need to do? No, I think it'll work. I think it'll work just fine. Yeah. So that all of this junk becomes 3 secant theta to the power 3. To the power 3. And what is 3 cubed? That was 27. Okay. All right. So that's all the setup. So that's what the denominator is going to end up becoming. Yeah. Yeah, that'll work. Sorry, I'm plugging in the trig identity in my head, because this becomes 9 tan square plus 9, factor out the 9, tan square plus 1 becomes secant. Yeah, that all works. Okay, now there is one additional complication here, in that we are taking a definite integral, and we have introduced a new variable, theta. So since our new integral is going to be in terms of theta, we have to change the lower and upper limits to be in terms of theta as opposed to in terms of x. So let's see how that's going to work. So when x is equal to 0, what does that imply for theta? Well, that means 2 times 0 is going to equal 3 tan theta. So 0, well, okay, divide both sides by 3. So that means tan theta is equal to 0. And also, the theta that we are picking is between negative pi over 2 and pi over 2. So what angle between negative pi over 2 and pi over 2 has a tangent of 0? Well, 0. There's only one theta that satisfies that, and it is 0. Okay, so the lower bound remains unchanged. What about the upper bound? So when x is equal to 3 root 3 over 2, what does that mean? Well, then 2 times x, so 2 times all of this, is going to equal 3 tan theta, right? I'm literally just plugging that in here. Let's see, so the 2's cancel, divide both sides by 3, so that's the same as saying that tan theta is equal to square root of 3. So let's see. Might have to break out your unit circle for this. So what angle gives us a tangent of root 3? What angle between negative pi over 2 and pi over 2 gives us a root 3? I think that is going to be pi over 3. Is that right? Because sine pi over 3 is root 3 over 2. Cosine pi over 3 is 1/2. Yeah. So that'll do it. Yeah, so break out your unit circle for this one. But there is only one angle between negative pi over 2 and pi over 2 that satisfies this, and it's pi over 3. Okay, so our new integral becomes the integral from 0 to pi over 3 of x cubed. Well, what was x? X is 3 tan theta over 2. So, how do I want to write this in a way which doesn't suck? 3/2 tan theta. Yeah, 3/2 tan theta, that works. And then we want to cube this, like so. And then on the bottom we have all of this junk. So the bottom becomes 27 secant cubed. Okay, and then instead of dx, did we ever do dx? Oh, we never figured out what dx is. So let's see. X is equal to 3/2 tangent theta. So that means that dx is equal to 3/2 secant square theta. D theta. D theta, like so. 3/2 secant square theta d theta. Yep. So plug that in here. Okie dokie. Now there is quite a lot of cleaning up that we need to do before we move on. So 3/2 cubed times 3/2, so that's 3/2 to the 4th power. And that's all over 27. So 27 is 3 cubed. So let's see. So we have 3 to the 4th over 3 cubed. So we just have a 3 left over. And then on the bottom, we have 2 cubed times 2, so that's 16. And then 2 of these secants cancel. So we have tan cube on top and secant, just a single secant on bottom. Like so. Sorry, I'm just double checking. Yeah, we're good. Yeah, 3/16. Okie dokie. So now we are sort of in a similar situation to where we were at over here, where, well, I don't really know what to do with these secants and these tangents, but at the very least I know I can convert these into sines and cosines. So let's just do that and see what happens. So let's see. So tan cube becomes sine cube over cosine cube. So sine cube over cosine, whoops, over cosine cube. As for secant, well, secant is 1 over cosine. So here we have 1 over cosine. So that's just cosine. Now one of these cosines cancels, so we end up with, I'm just going to copy paste this now. So one of these cosines cancels, so this goes away, and on the bottom we have cosine squared. Okay, well, maybe we're getting somewhere. So what can we do with this? Oh, that's interesting.